I have here a terminal and a PDF, the page of the PDF that listed the homework. So let's go ahead and recreate this. As you can see, I have this hhkchan.mod file in this directory, but this directory is a bit messy. So why don't I create a new one? I'll call it homework. And I'll change into that. And I'll copy the hhkchan mod file into this new folder. Okay, and I will compile it. Okay, so we have seen that the compilation was successful. Now if I start from Neuron import HGUI. Okay, so what is it I want to do? I want to make a model cell with a cell builder. And I want it to have a single section, which it will have. I want its geometry to be based on area. And by default, it will get an nseg of 1. I want the area to be 100 square microns, which is what I get by default. For biophysics, I want to have, aside from specific membrane capacitance and the cytoplasmic resistivity, I want to have Hodgkin-Huxley and this HHK mechanism present. And the only parameter I need to change is to start by reducing the conductance of the new potassium channels to 0. So all I have left is the Hodgkin-Huxley sodium and potassium channels. And at this point, I might as well save a session file. Cell.sys. And now I can create an instance of it. And now I will bring up a run control. Let me pull this down here so that it's out of the way. A run control panel, a voltage axis graph. And I'll make a point process manager with an eye clamp. Starts at 1 millisecond, duration of 0.1, amplitude of 0.1. And run a simulation. Okay, I will change t-stop. I'll make it be 20. Okay. All right, so at this point, got a spike. Looks normal. And we want to knock out the Hodgkin-Huxley potassium channels. And if we do that, we do it on the biophysics page here, going to HH. I'm going to change the potassium channel density from 0.036 to 0 Siemens per square centimeter. And now if I run a simulation, I see that first of all, membrane potential isn't stable. The cell really doesn't want to sit at minus 65. And furthermore, I see that if I do inject a stimulus current, the cell just immediately goes way up to the sodium equilibrium potential, approximately. What is ENA? Let's see what ENA is. Oops. ENA is not defined. So it's going to be H.ENA. Okay, so it's a range variable, and it's going to be soma, soma at 0.5 ENA. Ooh, soma is not specified. That's because I didn't create it with Python, I created it with Hoke, so its Python name starts with an H. Ta-da! Finally, miraculously, I stumble into the complete and proper name, the proper Python name for this variable. We knew that it was sodium equilibrium potential, so we knew that ENA was going to be in there somewhere. If we were working in Hoke, it would belong to the soma, and not only that, but ENA in Hoke would have been a top-level variable that we would have been able to see without doing anything more. But in Python, it's not at the top of the Python interpreter. Instead, Python has to get the value from Hoke, and ENA besides doesn't even belong to the top level of Python. It's not going to be it's not going to be accessible as h.ena. Instead, it's ENA that belongs to the soma section, actually to a particular segment. Each segment has can have a different value of ENA because the ENA is a range variable. Okay, and it's automatically created when you insert a mechanism into a section that has a use ion NA statement. So when you insert a mechanism whose end model code contains a use ion statement, this is a clue to Neuron that if you insert this mechanism into a section, that section better have that ionic mechanism. So Hodgkin-Huxley has two use ion statements in its hh.mod file. One is a use ion NA, and the other one is a use ion K statement. So when you insert Hodgkin-Huxley into a section, automatically that section knows about ENA and EK. All right? Because it now has an ion channel that has use ion statements for sodium and for potassium. All right. But even knowing that is not enough for us to be able to discover the value of ENA, because soma is not a Python thing. Soma is a Hoke thing, and for Python to know its name, you have to put h dot in front. Okay, so that's a lot of notation to have to use to access the value of ENA. And if we were going to be doing that a lot in our Python program, what I might want to do is to start off by saying that that soma, a Python thing called soma, is equal to h dot soma. And that makes this Python word soma be an alias for the Hoke section, soma. So that now I can say soma 0.5, open close parens, dot ENA, and I don't have to put the h dot in front of it, okay? So remember, if you are creating your sections in Hoke, because you're using somebody else's old Hoke code, or because you're using a session file exported from the cell builder, then you can get nice looking Python names for all of your sections by just using h dot and the Hoke name and assigning that to a Python alias. Okay, so here we have now, finally we know the ENA at the middle of the soma, and we see that when we try to make our model cell fire a spike, membrane potential zips regeneratively up to a voltage which is way up there. How big is it? 48.86 millivolts. And that tells us that, well, it didn't get all the way up because why? Because we still have leak channels. And because the leak channel conductance is not zero, and it's not infinitely small compared to the sodium channel conductance. Okay? So at the very peak here, almost all of at the very peak here, the membrane conductance is mostly sodium channel conductance, and that's why we're so close to the sodium equilibrium potential. Okay, and leak. Well, what's e-leak? H dot soma 0.5 leak dot e. Am I right? Ooh, it doesn't have that. It's hh dot leak dot e. Whoops. HH, no, has no attribute leak. So it's HH dot E leak. Oh, what about that? Huh. What actually is the name of that parameter? Let's go back to our cell builder, biophysics page. It's EL. How about that? Using the totally wrong name all along. So it should have been hh.soma 0.5, excuse me, h.soma 0.5 HHEL. Ah, finally, we discover the Python name for this. Okay. Could I have done this in a different way? Well, it doesn't show me, well, it shows RA. It shows HH. No, doesn't show me that. Okay. All right. Well, when you get to Robert's part of the course, you'll find out a lot more about model introspection with Python. But in any case, we know what the leak potential is. It's minus 54.3. So why do things settle out at about 0? Let's go further out in time. Let's go out to 200 milliseconds. And let's see what that finally is. Final value is really close to 0 millivolts. Okay. And why don't we see what the leak current and the sodium current is? What both of them are. Okay. So if we were to plot those, graph current axis, plot what? Soma. Is iLeak HH available? It is. Good. Accept. And I can see what it's called. Move text. Click on the label, move it. There we go, back to crosshair. And I can also do the same for plot what? For IK. Notice I could plot IKHH, but there's only one potassium current here anyway, so I might as well call it IK. That's the total potassium net potassium current from all channels that allow potassium to flow through them, for all channels in mechanisms that use ion K, write IK. Okay, so now I can move this label. Whoops, that's going to be 0. Move text. And I can also do the same thing, plot what? For INA. Accept. I'm going to move that as well. Okay. So now what I'm going to do is I'm going to do color brush to make these lines stand out better. Red and thick is going to be sodium. Blue and thick is going to be potassium. And black and thick is going to be iLeak. Okay, the leak current. Okay. Crosshair. And do a knit and run. Aha. Let's do view equals plot. And we see that initially there's a very big current from all of these, and then if I move these labels, all right, and we see that IK is in the middle here. It looks like it's going to be 0, which it should be. Let me do a set view so I can zoom in on this. It looks like I need to go into minus 0.05 to 0.05. Okay. And those are our 3 different currents. Crosshair, crosshair, potassium current we'll get to next. This is the leak current first. Potassium current is next. And the sodium current is last. So let's look at what values were printed in my terminal here. So the first one I did was the leak current, which is 0.16. What are the units here? What are the units of conductance? Milliamps per square centimeter. Okay, that's a unit, neurons density units for ion channels are milliamps per square centimeter. So that is 0.016108 milliamps per square centimeter. It's positive because it's an outward going potassium, outward going leak current. Our potassium current is 0, exactly 0, because we don't have any potassium channels that are open. They're all gone. There's no potassium channels there to open at all. And here we see the sodium current is minus 0.016108 milliamps per square centimeter, exactly identical and opposite. So let me see HH.SOMA 0.5 INA, whoops, H.SOMA. Let me just call that SOMA 0.5 because I've made a Python alias. So there's the sodium current in the middle of the SOMA. And there's the potassium current in the middle of the SOMA. That's the current density. And what about the leak current? IL. It has no attribute IL. Look at that. It's called IL underscore HH. Well, that's why we can't do it. So it's HHIL for Python notation. Okay, so we see here that's the numerical value of the Hodgkin-Huxley leak current. That's the numerical value of the Hodgkin-Huxley sodium current. Let's see if they add up to 0. Aha. The Hodgkin-Huxley leak current plus the Hodgkin-Huxley sodium current add up to 0, which is pretty good. I think we can say that charge conservation is obeyed here. So indeed, this is the membrane potential. I'll just call it SOMA V. SOMA 0.5.V. That is the membrane potential at which the leak current is equal and opposite to the sodium current. Okay, so there we have it. And we're able to verify that these two currents are equal to each other, the leak and the sodium current, and that's why we have this resting potential. Okay. All right, so now what we've done is we've shown we have knocked out the potassium channel. Can we resurrect our spike? Can we recover a spike by restoring potassium channels that have identical dynamics, but which come from a different mechanism? So let's change this to, what should they be? 0.036? Let me just look. 0.036. So let's make this HHK's channel density be 0.036 Siemens per square centimeter. And now let's run a simulation. And let's go back to our 20 millivolts. Knit and run. Okay. Do view equals plot here. I'm going to do keep lines on this. Turn it off. I'm going to do keep lines on this. And in fact, I want to make this be a very thick trace. Color brush. It'll be black and very thick. Okay. Get back out of color brush. Back to crosshair. Okay, so there's our action potential, and there's our ionic currents using this synthetic potassium conductance. And if we get rid of that, knock it out, and re-express the Hodgkin-Huxley's native potassium conductance, potassium channels, doing a knit, and doing a knit and run, we're getting what looks like identical results. But I think we can show that in fact we did get something. Let me go right in here and do do color brush and let that be red. Or better yet, be dotted and red. Okay, crosshair. And I hope you can see here that now these lines are overlying each other, and you see black and red dots in this figure. Okay, it combines black and red. If I click on a knit, the red goes away. If I click on a knit and run, the red comes back, and that shows us that we have got the red trace is overlying the black trace that we got with the extrinsic potassium channels, the one that we inserted separately. So we were able to reconstitute the spike. We were able to knock out and rescue, and then knock out the rescue channels and go back to the original channels and get the spike. Okay, so we've done all aspects of this exercise, including confirming that the control and rescued action potentials have the same waveform. Okay, and we did that all using the GUI, and we could save figures for publication if we liked, using the print and file window manager to generate, if we wanted, a PostScript image or an iDraw image, or we could print numerical results from these various simulations by selecting one of these graphs and then doing print ASCII. Okay, and there's information about how to do that in the online, but I believe it's in the FAQ list, or it may be in a document for how to use the print and file window manager. Okay, which is also available online through the FAQ list. Okay, so there we have all of the things that we wanted to do for that exercise. Are there any questions about that? Okay. So let me now go to another topic. Remember that the session before last, we talked about linearity, and we showed that in fact that we had a model cell that even though it had voltage gated currents in its axon, soma, and apical dendrites, that for EPSPs whose peak amplitude was about a millivolt when the synapse was located at the soma, the cell acted in a quite linear manner. So at that point I mentioned that meant we could apply linear circuit analysis to our model cell, and that would help us understand how small signals on the order of the kinds of sub-threshold fluctuations that occur between spikes and before spikes and after spikes, how those are spreading throughout a model cell. Okay. So I'd like to follow through on what we discussed at that point. And what I'm going to do now is I'm going to actually jump to an example. I'm going to use the Neuron main menu. Not the Neuron main menu, I'm sorry, Neuron demo, Neurondemo. And I'm going to bring up that stumpy looking, that amputated appearing pyramidal cell. Okay? And it makes a spike, so it has active currents. Okay, and the active currents I happen to know are in the axon and the cell body, but all the rest of the cell is passive. And the fact that it's passive or active or any part of it is active isn't of any concern to us right now, except to say that it does have voltage-gated channels. Okay, what I'm now going to bring up a set of graphical tools that Neuron has for doing small signal analysis on such a model cell, on a branched model cell. So let's go down to, impedance. So under Tools, Impedance, and we're going to be using the Frequency tool. What does that mean? What does this tool do? This tool, if you have a model cell, this tool will allow you to place a recording electrode and a measuring electrode in the cell. And it starts out with both of those electrodes being at the middle of the root section. Okay, that's the section that has no parent. Okay, no parent of its own. Okay, and what we can do with that is we can see the impedance of the cell, input impedance or transfer impedance, as a function of where our electrode is. So in this case, I have a single electrode attached to the middle of the soma. I'm not using the other electrode because I'm injecting and measuring. It's as if I'm injecting and measuring current right at the middle of the soma. And what I'm able to do is see the input impedance at that location as a function of frequency. So the y-axis here is in megohms, and the x-axis is in log 10 of frequency in hertz. So 0 here, 0 on the x-axis means 1 hertz. This is a tenth, okay? Log 10 of 0.1 is -1, so this is 1/10 of a hertz. This is 10 hertz, 100 hertz, a kilohertz. So we can see that in this cell, the input impedance at low frequencies is about 20 megohms. I don't know if you can see that well there, but if I scroll across the top in crosshair mode and I click, I can see that the Y coordinate is pretty close to 20 megohms. And I can also see that if I drag this along, the input impedance starts to drop at around, 3 to 5 hertz, maybe 7 hertz. And by the time we get to whatever is antilog of 1.8, what is that? Anybody know the one place log table? Okay. Well, all right. 0.6 is 4. 0.9 is 8. 0.8 is 6.4. Antilog of 0.8 is 6.4. Okay. So let me see. Log 10, 1. A log 10 of 6.4 is 0.8. What else can we do? Well, we can move that to different points in the cell. And we see here, we move our injection and measurement site up here into the apical tree, and we expect input impedance to be higher. But how much higher is it? And that distance tells us the path distance from the origin of the cell to the point at which we are now measuring. So let's see what that looks like. View equals plot. Oh, we've more than doubled it. The input impedance of this cell is around 45 megohms up here in the apicals. Okay, if we go way out here into the apical tuft, the input impedance is more than 80 megohms. And furthermore, let's see what it is, 82, and where does it drop down to 41? Oh, also at about 6.4 hertz. Okay. Where does it drop to 0.7 times 81? It would be 56. Oh, 1.6, which is about, what am I saying? 50 hertz. That's 50 hertz. 1, yeah, that's 10 hertz. That's 50 hertz. Okay, let's go back to the soma. We're close enough to the soma. View equals plot. And we drop to half at about 64. And 0.7 is at about, actually, yeah, 0.7 is about 50 hertz. So that's 1 hertz, 10 hertz, 50 hertz. Okay. So we're able to see the input impedance of the cell at different locations. We can plot other things if we want. We can plot the log of voltage attenuation, and we can as a function of frequency. So what is the voltage attenuation from the soma, say, to this point in the apical dendrites? Or can we do that? Select location. We want to select the inject, and then we can select the measure. So I can click down here and get back to the soma. And let's make these select inject, back in the same location approximately. And we can then see what the voltage attenuation is if we wanted to. Let me do that better. Let me bring that up a new instance of this tool. Tool, impedance tool, frequency, everything is at the soma. If I want to see voltage attenuation, okay, logarithm of attenuation is 0, because if I apply a millivolt at the soma, I will measure a millivolt at the soma. The ratio is 1, the log of that is 0. If now I change the measurement location to, say, this point here, and I say I apply 1 millivolt here, and I want to see how big is it out here. Okay, what is the ratio of the voltage here to the voltage there as a function of frequency. And we can see that the attenuation is rather small. The log of attenuation is very small at DC. It's 0.39, and 0.39 corresponds to about 2.5. That means that the voltage here is going to be 2.5 times the voltage there. Attenuation gets bigger as you go further away. If I move the measurement point further in, V equals plot, and we see that if I am looking at the attenuation from the soma to that point, I'm looking at something that has a log of 0.07, which is very small attenuation. But as we move out into the tree, attenuation gets much bigger very quickly. Okay? All right. We can do other things with this tool as well, but this is not the most exciting tool. I'm going to close it, and instead, let's take a look at one that will tell us information about points on a path. Okay, now in this case, the tool shows us our shape of our cell, but we can specify a path that's of interest to us. So what if I want to see the input impedance of this cell? I clicked on plot ZN. I want to see input impedance of this cell over a path that starts at the distal end of this basilar branch and ends at the distal end of that apical branch. Okay, so I'm going to be plotting the input impedance over that path. Let me set the path start. It's going to be that distal end of that branch. So it's the one end of dendrite 7, bracket 5. Terrible naming convention. This cell is just a very odd anatomy file, so that's why it has these awful names. And then the distal end of the path. So that's one end of the path. The other end of the path I want to be up here. And of course this path goes toward the soma and then up the apical tree and out into that distal branch. And we want to see the input impedance, and it's going to be at a frequency of 0 hertz. Okay? Let me do view equals plot down here. And we see the input impedance of the cell along this path. And we see the input impedance is lowest when we're at the cell body, and it's highest when we get out into these distal branches. And it's very interesting, the basilar branches are so skinny that the input impedance at the distal end of this basilar branch, that's the one over here at the negative distances, is about as high as the input at the distal end of this apical branch. Okay, even though this apical branch is much farther from the cell body, and that's because this branch is extremely narrow. So we see the input impedance of the cell along this entire path. Oh, and I should mention that since this model cell has voltage gated channels, we should include the contribution that would result from gating of the ion channels. So even though you may have a very small voltage fluctuation in a cell, it will still affect the gating of the ion channels, even though the cell is in its linear range of operation. And you will see that effect on the input impedance of the cell and other measures of signal transfer. So we're going to include the fact that the channels can gate. I'm going to click on that checkbox, and you notice that did affect things slightly. Not much. Over here, you'll notice this branch now is going to jump down when I include the derivative of states, the time-varying derivative of states. And why is that? That's because the soma and the axon have Hodgkin-Huxley, and that's going to be affecting, that's going to be a load on the proximal end of this dendritic branch. It doesn't do much to this apical branch, but it moved this input impedance on this basilar branch a little bit down, okay? But that's it, that's for DC signals. What if we go up to 1 hertz? 1 hertz, not much. Go up to 5 hertz, 10 hertz, okay. What is the effect of gating when we're at 10 hertz compared to DC? Not much, but a bit more perhaps. Let's go up to 20 hertz. Aha! Not much effect. Those voltage gated channels don't have much effect. But we do see that when we go to higher frequencies, there's more leak of signal out of the cell. The input impedance of the cell gets smaller at higher frequencies. Why would the input impedance of the cell get smaller at higher frequencies? Anybody have an idea? Well, because how does signals leak out of the cell? If I'm injecting a signal into the cell, how does it leak out? It has to go through the cell membrane, right? And at DC, the only way it can get through the cell membrane is by flowing through the ion channels in the membrane. At very low frequencies, that's still the only way it can get out of the cell, is basically by flowing through the ion channels in the membrane. But as we go up to higher frequencies and higher frequencies, membrane capacitance allows more and more of the signal to escape. So at the higher frequencies, membrane capacitance makes the cell more leaky to signals, which is why at higher frequencies attenuation is more severe. Okay? So that's why we're seeing so much more attenuation, I should say, so much of a smaller input impedance than we did at DC. Here's the DC input impedance, and there's the input impedance at 20 hertz. It doesn't look like a big difference, but when you get much above 20 hertz, let's try 50, it gets bigger and bigger. So here it is at 50 hertz. Let's do a keep lines. And here it is at, let's get out of keep lines now. And here it is back at DC. And you see how much the input impedance drops when you go up to higher frequencies. Well, what do these frequencies relate to? Well, what's the membrane time constant? The membrane time constant is the product of the membrane capacitance and the membrane specific resistance. Okay? And in this model cell, the membrane time constant, let's take a look at, well, we really can't do that here, unfortunately. There isn't a nice discrete parameter. Oh, but wait a second. Let's see. We should be able to discover it. This is dendrite 129. Dendrite 129. Those H dendrite 1 bracket 29.
But is this in Python?
Oh, I'm sorry. This is in Hoke. My mistake. I can just do dendrite 129. I'm so used to Python. P section. And it'll tell me that the passive conductance is 1e to the minus 4 Siemens per square centimeter, which means our membrane time constant is only 10 millisecond. Okay? Well, when you have a membrane time constant of 10 millisecond, that means that your membrane has equal capacitive and ionic conductance at a frequency that corresponds to that time constant. Okay, it's 0.01 seconds is tau m here. F is 1 over 2 pi times 0.01. The frequency at which membrane capacitive current is equal to membrane resistive current is 1 over 2 times pi times tau m in seconds. And so tau m in seconds, tau m is 0.00, tau m is 10 milliseconds, which is 0.01 seconds. And that frequency is 15 hertz. So at frequencies above 15 hertz in this model cell, half of the signal leaking out of the cell is leaking through membrane capacitance, and the other half is leaking through ion channels. And that's not a very high frequency, about 16 hertz. Okay, so we start to see changes in input impedance before that, and by the time you get much past 15 hertz, most of the leak from the cell is going to be through those channels. And if your cell has a membrane time constant of, say, 20 milliseconds, which an awful lot of neocortical cells do, that means a critical frequency of about 8 hertz. Okay, so capacitive signal loss through cell membrane is a big deal in most cells at frequencies that are relevant to spike generation and EPSP propagation. Because remember, spikes are on the order of a millisecond long, and EPSPs are on the order of maybe 5, 10 milliseconds long, and those are very short times compared to 16 milliseconds. I should say, compared to membrane time constant, which is 10 milliseconds. Okay. All right, so let's take a look at one of the other impedance tools. The shape tool. What we're doing here is we're calculating the attenuation of signals spreading, in this case, away from the cell body. The experiment in this case is I'm injecting 1 millivolt signal at the cell body, and I'm seeing how much attenuation there is as I go out on each of these different paths, and I'm redrawing that path with a length that is proportional to that attenuation. So the more attenuation, the longer the path becomes. The less the attenuation, the shorter the path becomes. And if I redraw this cell in this way, this is one length constant. And that means if you go that far along any path, you're talking about an E-fold attenuation. Okay, so that if I put in a millivolt here, the potential here will be approximately e to the minus 1 times a millivolt. If I have a millivolt signal there, and the potential there will also be about e to the minus 1. Actually a little bit not quite as attenuated. And this is just at DC. And if we go up to higher frequencies, we see that attenuation will increase, and our cell will be redrawn with longer and longer branches. But the interesting thing here you'll notice is these basilar branches are extremely short, even at this high frequency, meaning that whatever fluctuations are happening at the cell body are very efficiently spreading into the basilar branches, rather poorly spreading into the axon, and also very poorly spreading back up into the trunk. Okay. If we turn around the direction of signal flow, and now let's say we have signals propagating to the soma from, say, a synapse out on one of these branches, and then we were to draw the length of the branch, the length of the path, proportional to the amount of attenuation along that path, we'd get attenuation in the opposite direction. And here we'll see that the cal bar for an E-fold attenuation is down here. It's about that big. And we can see that the cell has much larger electrotonic extent for signals spreading toward the soma. There's a lot of attenuation for signals trying to spread from the apical tuft to the cell body, about e to the third power worth of attenuation. Likewise, from each of these longer basilar branch. So there's a lot of electrotonic attenuation for signals moving toward for voltages moving toward the cell body, and relatively little for voltage moving away from the cell body except along this apical trunk. Okay, now I think we all kind of understand why you might have trouble getting much of a signal through this narrow dendritic branch into the cell body. You have this very narrow pathway. It has a high series resistance in here. The membrane, there's not much membrane, so very little of the signal is going to leak out. But even so, there's such a big series resistance between here and here, and there's this huge electrotonic load at the cell body. Because once a signal gets from here to here, it doesn't just stay in the membrane capacitance in the cell body. It can run out into the apical tuft. It can run away into these other basilar branches. There's a giant load on this end of this little branch. And that means that when we try to force a current from here into the soma, when we try to do that, we're going to be losing a lot of that out into these branches. Okay, so a lot of the voltage, we can apply a very high voltage change here. We'll only get a very small voltage change there because there's such a big electrical load at the soma. Okay, so you can use this tool to explore electrical signaling properties in these cells and discover for yourself things like, if I'm voltage clamping the soma, how well can I control what branches? And for that, we want to see voltage transfer away from the soma, V out. And if we're voltage clamping the soma, we can see that even at 30 Hertz, we have pretty good control over all the basilars. Pretty good voltage control. Where we don't have good voltage control is into the axon or the apical tree. All right. One reason why we don't have good voltage control of the axon is the axon has Hodgkin-Huxley channels, and Hodgkin-Huxley channels have a leak conductance which is on the order of 3 times bigger than all the other branches do. And so a lot of current leaks out of the cell between here and the distal end. So we don't get good voltage control of these other branches. Okay. If on the other hand, we're interested in how well do we see an EPSP generated here? If a 1 millivolt EPSP is generated here, how much do we see here? We would do the VN transformation and see what those attenuations are. Okay, so there's some information about this tool, and you can explore that on your own. These are called the Impedance Tools, and there is an online tutorial about them, which is available at Neuron's website. No, let's go back. Under documentation, okay, and there are some tutorials here, and one of them, ta-da, 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 I don't see it here. Cell Builder Import 3D. One of them should be for the impedance tools. And I just don't find it. Let's go to the exercises from the 2018. There we are. So I found it finally. It's in this electrotonic analysis exercise from the 2018 Neuron Summer Course. And this introduces you to the various tools. The frequency tool, which we looked at briefly, the path tool, the log A versus X tool we haven't talked about, but that's more quantitative in its results, and the shape tool. And you can work your way through that exercise if you're interested in small signal signaling in cells, in model cells. Okay, so anybody who's doing wet lab experiments with microelectrodes is probably going to be interested in this. If you're interested in synaptic integration, you're going to be interested in this. If you're interested in transfer impedance and what that means and how it's relevant to neuronal operation, you'll be interested in this tutorial. And what I will do is I'll mention this location in the Slack chat. Okay. All right. Are there any questions at this point? Well, if there are no questions, then I think what I will do is I will go ahead and include a mention of the electrotonic analysis tools in the Slack chat, and let you go on your way. And we will be having another session on Thursday. This time, Robert is going to be doing a presentation, and I look forward to seeing what kinds of discussion and questions arise from that. If you have questions about anything we've done today or previous sessions, please be sure to contact us. Slack chat is fine, email is fine. And again, we'll see you on Thursday.